So what we're looking at then is applying this control volume to a pipe with heat transfer, and we're going to be looking at the heat as it's transported through a cylindrical control volume. So the volume here is 2 pi r delta z. All right, and so what we'll have is this is the length, delta r. Into this control volume, we'll have Q is the heat flux times the surface area, so be evaluated at R. Our flow will be through this control volume, and coming out of this control volume, we'll have Q equals the flux times the area evaluated at R plus delta R. All right, so we know we should write this now before I make a mistake here, that this AS is, so this is going to be 2 pi r delta z if this is evaluated at R, this surface area evaluated at R plus delta R equals 2 pi delta R plus delta R delta Z. So we know this surface area is actually going to be changing along with Q double prime as we move out of this system. So we're going to write, let's just write a balance with Q. So into this control volume, we have Q. Out of this control volume, we have Q. In is evaluated R, out is evaluated R plus delta R. All right. Excuse me. All right, so let's see. I am going to take this equation. We have Q evaluated at R minus Q evaluated at R plus delta R equals 0. And the lack of generation and accumulation we've seen for 1D diffusive fluxes that Q of R minus Q of R plus delta R equals to 0. We have an equation set up just like this. So I'm going to divide by the delta R length scale. And really, I'm going to take this limit and say that we have state 1 minus state 2 negative dq dr equals 0. Let's take the balance this way. Fourier's law, written for Q, is let's see, we have negative k as dt. In this case, we're moving along in R dr. All right, so let's replace this in for Q. Equals to 0. And so now we can say if K is a constant material property, we can remove that from this differential. And the surface area that we're interested in, we've taken the limit as delta goes to 0, so there aren't really two surface areas to speak of. And that surface area can be written as 2 pi r delta z. So let's remove k. And we can write this as a 2 pi r delta z. And dt dr equals to 0. And we can say, well, if k times this expression is 0, k is non-zero, so this term must be 0. Again, we can pull out 2, we can pull out pi. The delta z doesn't change with respect to r, so we are left with just r inside of this equation. So where we've landed, which is a little bit different than what we've seen before, is if we make those cancellations, we have ddr of r dt dr is 0.